The man who destroyed the Soviet Union's most important pipeline never touched a single valve. He never set foot in Siberia. He never wore a uniform, never fired a weapon, never attended a single briefing about the operation he was running. He sat at a desk in Virginia, drank bad coffee from a paper cup, and wrote code. And somewhere inside that code, buried so deep in the control logic that you'd have to know exactly where to look to find it, he flipped a single comparison operator. One character, a less than sign where a greater than sign belonged. That was all. That was the entirety of the weapon. 3 years later, on a night in 1982, the largest non-nuclear explosion in the recorded history of the Cold War lit up the Siberian sky so bright that an American reconnaissance satellite, orbiting 400 miles above the Earth, had its sensors overwhelmed. The analysts who first reviewed the imagery reached for phones with red handles. They were certain a nuclear device had been detonated. They were wrong. What had just detonated was something far more interesting. A trap that the Soviet Union had spent years and millions of dollars building for itself, with no idea it was doing so. This is the story of how the CIA turned the Soviet Union's greatest strength against it, and how one engineer, brilliant and sincere and completely deceived, was the instrument of his own country's undoing. To understand the scale of what happened, you have to understand what the Soviet Union was actually trying to do in the 1970s. Not the propaganda version, not the caricature, the actual strategic logic, which was coherent and, in its own way, impressive. By the late 1970s, the USSR had a problem that its leadership understood with great clarity and discussed with almost no honesty. The problem was this: the Soviet system could not innovate. Not in the organic, chaotic, market-driven way that Western economies innovated. The incentive structure simply wasn't there. In the West, an engineer who solved a difficult problem and brought a better product to market could become wealthy, could become famous within the relevant professional circles, could attract resources and talent that let him solve even harder problems. The system rewarded successful innovation with more capacity to innovate. It was a flywheel, and by the 1970s, it was spinning very fast. In the Soviet Union, the flywheel didn't exist. Engineers were salaried employees of the state. The state did not reward individual brilliance. It rewarded compliance with the plan. The plan specified production targets, design parameters, delivery timelines. Your job was to meet those targets, those parameters, those timelines. Not to improve them, not to propose alternatives, not to come back from a conference in the West with ideas about doing things differently. Meet the plan. Sign the report. Go home. Innovation requires the freedom to fail. The Soviet system had absolutely no tolerance for failure. So the Soviet leadership did what any rational actor does when they cannot build something themselves. They bought it. Or, more precisely, they stole it. The apparatus that executed this theft was called, internally, Line X. It was a division of the KGB's Intelligence Directorate, a global network of moles embedded in Western defense contractors, double agents burrowed inside American research universities, corrupted businessmen who could be trusted to look the other way while sensitive equipment disappeared into diplomatic pouches headed east. Line X wasn't interested in battlefield intelligence. It wasn't collecting information about troop movements or missile trajectories. It was systematically looting the entire intellectual and industrial infrastructure of the Western world. Blueprints for aircraft engines, formulas for specialty polymers, designs for precision machine tools, software, increasingly, critically, software. The scale of Line X was genuinely staggering. When its full operations were eventually exposed, Western intelligence analysts described it as the most ambitious industrial espionage program in history. At its peak, Line X was running acquisition operations in a dozen countries simultaneously, maintaining relationships with hundreds of sources, some of them aware they were working for Soviet intelligence, many of them not, and channeling stolen technology back to Moscow at a pace that the analysts assigned to track it found difficult to keep up with. And they were good at it. The KGB officers running Line X operations were, in many cases, genuine professionals, patient, methodical, intellectually sophisticated. They understood the technology they were stealing well enough to know what was worth stealing. They developed relationships over years, even decades, with sources who didn't always know they were sources. They identified the precise points of weakness in Western export control systems, the gaps in customs enforcement, the underpaid inspectors, the bureaucratic confusion that came from having 16 different agencies theoretically responsible for preventing exactly this kind of theft, none of them talking to the others. For years, by almost any objective measure, they were winning. Inside the Politburo, the reports from Line X were received with enormous satisfaction. Here was a solution to the innovation problem that fit perfectly within the Soviet ideological framework. No messy market incentives required, no concessions to individualism, no private profits. Just disciplined collection, systematic analysis, and implementation. It felt, to the men who ran it and the men who funded it, like proof that the Soviet system worked. That discipline and organization could overcome any obstacle, even the obstacle of not being able to invent things. They were not entirely wrong. The stolen technology worked. The Soviet industrial programs that ran on a foundation of Western blueprints and formulas and software were genuinely functional. They were behind, always behind, because the theft introduced lag time, and the implementation introduced further lag time, and the Western originals kept advancing while the Soviet copies were still being decoded, but they worked. The arrogance this bred was real, and it was deep. By the late 1970s, the senior KGB officers running Line X had developed a conviction that they had cracked the problem of Western technological superiority. Not solved it, cracked it, found the exploit, identified the vulnerability that made all of the West's innovation lead irrelevant. They could steal faster than the West could advance. They could acquire in months what had taken years to develop. They were, in their own self-conception, untouchable. They had no idea that every piece of technology they had ever stolen had been cataloged, that there was a list, that someone had given that list to their enemies. His name was Vladimir Vetrov. His code name, in the files of French intelligence, was Farewell. And in 1981, he walked into a meeting with an officer of the Direction de la Surveillance du Territoire, French counterintelligence, and handed over the entirety of Line X's operational records. Vetrov was a senior KGB officer stationed in Paris. He was not, by any account, a particularly dramatic figure. He was not driven by ideology. He didn't appear to have strong feelings about communism versus capitalism. He was not driven by money, at least not primarily. What drove him, as best as historians have been able to reconstruct from his own statements and the analysis of those who handled him, was something closer to professional disgust. He had spent his career inside the KGB, and he had arrived, somewhere in his 50s, at the conclusion that the institution he had served was profoundly corrupt, profoundly incompetent, and profoundly contemptuous of the people who worked for it. He wanted to burn it down. He had the means to do so. What Farewell brought with him was not intelligence in the usual sense. It was not information about a single operation, a single asset, a single plan. It was the complete architecture of Line X. The acquisition targets, the methods, the assets, the results. Hundreds of pages of documentation showing, in precise detail, exactly what the Soviet Union had stolen from the West, through which intermediaries, and for what purposes. The French shared it with the Americans, who received it with the controlled excitement of professionals who have just been handed something they didn't know they needed until they saw it. The initial American reaction was satisfaction, quickly complicated by a deeper strategic problem. The Farewell dossier told them what the Soviets had stolen. It told them which Soviet industrial programs were now built on a foundation of Western technology. And it raised a question that did not have an obvious answer. What do you do with this information? The conventional answer was simple. Use it to roll up the network. Identify and expel the Line X officers. Arrest the cooperating businessmen. Shut it down. Declare victory. Write the press release. But a small group of people in the Reagan administration, including National Security Council staff members who had spent considerable time thinking about economic warfare as a strategic instrument, arrived at a different answer. A more elegant one. What if, instead of shutting the pipeline down, they let it run? What if they let Line X keep stealing? What if they fed it? And what if the technology Line X was stealing was subtly, carefully, deliberately broken? The idea was elegant in the way that the best traps are elegant. It used the adversary's own capabilities against them. Line X was effective because it was systematic, because it operated at scale, because it moved quickly. All of those strengths, in this scenario, became vulnerabilities. The same network that could acquire stolen technology rapidly and distribute it across Soviet industry could, if fed sabotage technology, distribute that sabotage rapidly and at scale. The Soviet system's tendency to implement acquired technology without asking too many questions about its provenance, a tendency born of necessity, since you couldn't exactly call the manufacturer's technical support line, meant that the sabotage would be implemented without the scrutiny that might catch it. The operation was not simple to design. It required solving several problems simultaneously, each one capable of causing the entire thing to unravel. The first problem was selection. They couldn't corrupt everything. If the Soviets acquired a dozen pieces of sabotaged Western technology, and all 12 of them failed catastrophically within months, even the most arrogant, blinded analyst in Moscow would conclude that something was wrong. The sabotage had to be selective, targeted, and above all, timed. Some failures needed to happen quickly, fast enough to cause disruption and loss of confidence. Others needed to be delayed, building silently inside Soviet systems for months or years before triggering, so that the cause would be nearly impossible to trace. The second problem was authenticity. The technology had to be good enough to pass scrutiny. Soviet engineers were not stupid. They had, in many cases, excellent technical educations. If the sabotage software or hardware was obviously defective, if it failed simple diagnostic tests, if its architecture was clearly wrong, it would be detected immediately and discarded. The sabotage had to be invisible. It had to work correctly under all normal testing conditions. It could only fail under specific operational conditions that would not be encountered during standard testing. The third problem was deniability. If the operation was ever discovered, if a Soviet engineer ever traced the failure back to its origin, the Americans could not be directly implicated. The sabotage had to look like an error, a design flaw, the kind of mistake that legitimate software contains, because all software contains mistakes, and because no one who acquires stolen code has any guarantee that what they've stolen is perfect. These three constraints, selectivity, authenticity, and deniability, define the parameters of what the team had to build. And it was in the intersection of those three constraints that someone, working through the technical requirements of the Siberian pipeline project, identified the single, most elegant point of intervention. The pipeline itself was called Urengoy, Pomary, Uzhgorod, for 1,450 kilometers, the largest natural gas pipeline ever constructed. It began in the West Siberian Basin at the Urengoy gas field, one of the largest natural gas deposits ever discovered, and ran west and south, crossing the Ural Mountains, threading through the industrial heartland of the Soviet Union, and ultimately connecting to the gas distribution networks of Eastern Europe. If it worked, it would generate foreign currency revenues that would underwrite the Soviet economy for generations. It would give Moscow energy leverage over every European nation connected to it. It was not merely an engineering project. It was a geopolitical instrument of the first order. It was also running into serious technical problems with its control systems. A pipeline of this scale is not a simple piece of infrastructure. It's a dynamic system with thousands of interacting variables, pressures shifting at hundreds of monitoring points simultaneously, dozens of compressor stations that have to coordinate their output in real time, flow rates that change with demand and temperature, and the physical condition of the pipe itself. Managing this system manually is not possible. You need software. Good software. Software that can process sensor data faster than any human operator, model the behavior of the system in real time, and issue commands to compressor stations before pressure buildups develop into structural problems. Soviet engineers could not write this software in the required time frame. This was not a matter of general incompetence. It was a consequence of the specific history of Soviet computing, which had prioritized certain areas of development at the expense of others and had fallen behind in precisely the areas that pipeline management required. They could write software for ballistic missile guidance systems, which operated in controlled environments on deterministic inputs. They could not write software for a complex, chaotic, real-world system that needed to manage uncertainty and respond to conditions no one had anticipated. Line X was tasked with solving this problem, and they did. Vladimir Antov, the engineer who had been living with the pipeline project for years, who had spent countless late nights in his Moscow office with engineering drawings and cold tea working through pressure differentials and compressor specifications, received the stolen software through channels he understood to be irregular and did not ask about. The documentation was comprehensive, dense. It had the particular quality of technical literature produced by an organization that had never had to make its products accessible because the organizations that bought them were large enough to employ people who could handle complexity. He spent 3 days reading it before he allowed himself to feel the thing he had been suppressing since the package arrived. Relief. Not just relief, vindication. He had argued, in meeting after meeting with superiors who outranked him significantly, that the right approach to the pipeline's control problem was to acquire Western technology and adapt it. He had been questioned about this position. He had been told, in the courteous but unmistakable way of Soviet institutional hierarchy, that his advocacy for Western solutions was being noted and was not viewed entirely favorably. He had made the argument anyway, because the argument was correct. Now, holding in his hands what was represented to him as state-of-the-art Western pipeline control software, he felt the particular satisfaction of a man who has been vindicated by events. He was right. The system would work. The pipeline would work. Because he had pushed for the right solution when pushing had not been comfortable. He had no idea he was holding a weapon pointed at himself. Testing proceeded over several months. The results were excellent, which is to say, they were exactly what the team in Virginia had designed them to be. The control logic functioned precisely as documented. Pressure regulation responses were smooth and appropriate. The compressor stations accepted commands from the central system without detectable latency. The diagnostic routines returned clean results. The Soviet engineers who reviewed the system's performance, competent people, looking hard for problems because they understood the stakes, found nothing wrong. Antov submitted his report to the Pipeline Oversight Committee. The software was ready. What he did not know, and what his testing was specifically designed never to reveal, was what the software did under conditions of sustained high-load operation, conditions that would only arise after the pipeline had been running at full capacity for months, conditions that no testing protocol, however thorough, would encounter because testing protocols operate over days or weeks, not the months required to push the system into the operating range where the hidden logic activated. The thing hidden inside the code was not dramatic on its face. It was not a command to open valves and trigger an explosion. It was something more technically elegant and more merciless than that. It was a sign error in the pressure regulation function. Under normal operating parameters, the function worked correctly. When pressure rose toward a threshold, it reduced compressor output, bleeding off the pressure before it became dangerous. But above a specific threshold, a threshold calibrated to be just beyond the range that testing would explore, the comparison reversed. When pressure exceeded that threshold, the function interpreted the reading as evidence of a system inefficiency and increased compressor output to compensate. It pushed harder precisely when it should have pulled back. It was a feedback loop pointed in exactly the wrong direction, and it had only one possible endpoint. The pipeline went into full operation, and for months it worked. Throughput targets were met. Pressure readings were consistent. The compressor stations were responding correctly to central commands. The foreign currency revenues that the project was supposed to generate began appearing in the quarterly reports. Antov allowed himself a guarded satisfaction. The kind of satisfaction that a man who has been right about something difficult learns to keep mostly private, because the habit of restraint, once acquired in a Soviet ministry, does not easily leave. For months into full capacity operation, the pressure in a critical section of pipe exceeded the designed threshold for the first time. The software registered the anomaly. The operators in the monitoring station looked at their displays. The readings were slightly elevated, but within the range of normal operational variation. Nothing that required immediate action. The software was managing it. The system was doing what it was supposed to do. The software told the compressor stations to increase output. The pressure rose further. The operators noted it and returned to their other tasks. The readings were high, but not alarming. The software was responding appropriately to the conditions, or so it appeared. The software registered the increased pressure and responded according to its logic. More output. Push harder. The compressor stations complied. There was no alarm system capable of overriding what was happening, because what was happening looked, from every monitoring interface available to the operators, like normal system operation. The software was doing exactly what it was programmed to do. It was doing it correctly, without error, without malfunction. There was no bug to detect. There was no anomaly in the system logs. There was only a pipeline, running at pressures its designers had never intended it to reach, being actively driven further beyond those pressures by control software executing its instructions with perfect fidelity. The pipe held for longer than it should have. The steel was good. Soviet metallurgy, in certain applications, was excellent. But there are physical limits that no material can exceed, and the software was relentless in its logic, its terrible, inverted, flawlessly executed logic, and eventually the pressure reached a point where the steel had no answer. The explosion, when it came, was instantaneous. The natural gas released under that pressure ignited immediately in the cold Siberian air, and the fireball that resulted, visible from space, overwhelming the sensors of a satellite built specifically to detect nuclear detonations, was estimated at 3 kilotons of explosive force, the equivalent of 3,000 tons of TNT, larger than many tactical nuclear weapons. No one in the control room survived. The pipeline, 4,000 kilometers of it, the iron backbone of Soviet energy policy, the instrument that was going to secure Moscow's economic and political position for a generation, was destroyed along a critical section, with secondary explosions cascading through the compressor stations that had been faithfully executing their instructions to the very end. At Langley, the news arrived with the particular texture of information that confirms something you expected but hoped might not happen exactly this way. There was no celebration. The professionals who had designed the operation understood, with the clarity that only professionals achieve, that 3 kilotons is a very large explosion, and that the people who had died in it had not been the architects of Line X. They had been engineers and operators, people doing their jobs. This is the part of the story that the clean, elegant version tends to skip over. In Moscow, the aftermath was managed the way Soviet institutions managed catastrophic failures, with a combination of partial disclosure, strategic silence, and the particular Soviet talent for generating paperwork that acknowledged a problem while attributing it to causes that protected everyone involved from direct accountability. The pipeline explosion was attributed to material defects. Reports were written. Reports were filed. The reports were, by the standards of Soviet institutional culture, excellent reports. Thorough, well-formatted, completely inaccurate in their conclusions. The deeper problem, the fact that Soviet industrial facilities across the country were now running on software and hardware acquired through Line X, and that some portion of that technology might carry the same kind of hidden flaws as the pipeline control system. This problem had no clean solution. They couldn't admit it without disclosing the full scale of Line X's operations. They couldn't quietly replace all the suspect systems without triggering questions about why they were being replaced. They couldn't bring in outside expertise without the kind of exposure that was unthinkable. So they lived with it. And the uncertainty that this created, the silent, unacknowledged awareness that some of the systems they depended on might be wrong in ways they couldn't detect, was, in its own way, as damaging as any single explosion. It corroded confidence. It introduced friction into decisions about technology acquisition and implementation. It was the sand in the gears of a machine that was already running poorly. Antov learned the truth the way people in closed systems learn uncomfortable truths, in fragments, through implications, through the specific texture of conversations that stop when he enters the room. He would understand, eventually, that the software had not failed due to some operational anomaly he had failed to anticipate. He would understand that he had been used, that his expertise, his reputation, his years of advocacy for the right solution, all of it had been the mechanism of a trap he hadn't seen because the people who built the trap understood his motivations better than he understood theirs. He had believed that the right technology, properly applied, could overcome the structural problems keeping Soviet engineering behind. He had staked his professional reputation on that belief. He had delivered exactly the result he worked toward. The most advanced Western pipeline control software, installed in the most ambitious Soviet infrastructure project. It had worked. Perfectly. Exactly as designed. Just not by him. The farewell Dossier operation was declassified in stages over the 1990s and 2000s. Thomas Reed, a former National Security Council staffer in the Reagan administration, confirmed its outlines in his 2004 memoir. The precise nature of the software sabotage program remains partially classified. Colonel Vladimir Vetrov, farewell, was identified by Soviet counterintelligence and arrested in 1982, the same year as the explosion. He was tried for treason and executed in 1985. He never knew the full scope of what his information had enabled. He handed over the keys and never saw the door open. The pipeline was eventually rebuilt, rerouted, fitted with different control systems. It operates today. It has not exploded again. Somewhere in Virginia, in a building whose address is not publicly listed, there is presumably a file. Inside the file, among other things, is a printout of the function that controlled pressure regulation in the Siberian pipeline's compressor stations. The function is unremarkable, a few dozen lines of code in a language that most working programmers today would have to look up. The sign error is almost impossible to spot unless you know it's there. One character, a less than sign where a greater than sign belonged. The most expensive punctuation in the history of the Cold War.